This is how to derive the rules of exponents. I'm going to cover exponents to the 0 power, negative powers, fractional exponents, decimal exponents, exponents that both go in an ascending and a descending order, and I'm going to show some exponent scales, one of which I just made up, so I'm sure nobody's ever thought of it before. All right, first up, multiplication, division, exponents. A squared times a to the third. That means a squared means a times a to the third means a times a times a. Thus you get a to the fifth. You just add them, or you just add your exponents. Since multiplication, you add exponents, that means division, you will subtract exponents. If we take a squared divided by a to the fourth, that's the same thing as a times a. Quantity divided by a times a times a times a. The two a's on top will cancel out with two of the a's on the bottom. You end up with 1 over a squared, or a to the negative second. So when you have a squared divided by a to the fourth, that's 2 minus 4, so it's negative 2. You get 1 over a squared, or a to the negative second. If you don't want to do this in fractional form, you can do this in multiplication form. So a squared times a to the negative fourth. Add your exponents when you multiply, and you still end up with a to the negative second. And next page. When you take an exponent to an exponent, so a squared, quantity to the third, then you multiply your exponents, so you get a to the sixth. The logic is a squared means a times a. You take that quantity to the third power, so that means you take a times a 3 times, and you end up with a to the sixth. When you have an exponent to an exponent to an exponent, so in this case we have a to the second, quantity to the third, quantity to the fourth, you still multiply all your exponents together. So 2 times 3 times 4 equals a to the 24th. Notice what we're doing here is we're starting with the base, and we keep increasing that base. So we start with a as our base, and then we square it, which gives us a new base that's even larger. Then we take that new base to the third power, and that gives us an even larger base. And then we take that larger base to the fourth power. You use this method when you're nesting, which means you're putting one function inside of another function, or one term inside of another term. I showed how to do this right here. So you can take a to the second, quantity to the third, so that's a to the sixth. Then you take that whole thing to the fourth, and you get a to the 24th. So here's how the nesting works. I used this nesting technique when I did a video on radius of a planet versus its gravity. So you can see that video if you want, but here's the gist of it. Here's how the nesting works. You take a times b, quantity to the second, equals c. Notice these letters go in order: a, b, c, d, e, f, and g. So you take a times b, quantity squared to get c, c times d, quantity cubed to get e, and then e times f, quantity to the fourth, to get g. We can take this whole term here for c, which is a times b, quantity squared, insert that into c right here. So we end up with a times b, quantity squared, times d. And that's what we have right here. And then that quantity will be cubed to get e. Then when we look at this function here of e times f, quantity to the fourth, to equal g, we can insert this whole function right here for e into that function. So we end up with a times b, quantity squared, times d, then that whole quantity squared, or sorry, that whole quantity cubed, and then times f, and then that whole quantity to the fourth power. Thus, our term here for c, which is a times b, quantity squared, is nested inside this function where it's multiplied by d, and then that's nested inside this function where it's multiplied by f. And remember, this is the logic for going up on your exponents, where you start, if you have a to the second, and then to the third, and to the fourth, you go up and you multiply 2 times 3 and then times 4. On the next page, I'll show what happens when you go down on your exponents. I'm going to use some really small numbers here to show how quickly this thing gets out of hand. If you have a to the third power, then that's to the third power, and then that's to the third power. Since there's no parentheses here, you start with the top exponent and work your way down. So 3 to the third power equals 27. That means you have a to the third power. So then you take that 3 to the 27th power. 3 to the 27th power equals about 7.6 trillion. So we have a to the 7.6 trillion. I don't know when you would use this type of notation, because there's only about 10 to the 80th number of atoms in the known universe, according to our current understanding. So if you were to take 10 to the 7.6 trillionth power, divide that by 10 to the 80th power, you subtract your exponents, that's 7.6 trillion minus 80. You're still going to end up with about 7.6 trillion as an exponent. That would mean that you will need 7.6 trillion universes, the size of ours, to obtain that number of atoms. Just for comparison, you can take 2 to the 1,000th power, and notice 1,000 is quite a bit smaller than 7.6 trillion, but 2 to the 1,000th power even is about 10 to the 300th power. And again, this is a very small number, 2, and then taking that to the exponent of 1,000, that's a very small number compared to 7.6 trillion, but we still end up with 10 to about the 300th power, which means you would need about 220 universes to get that number of atoms. And none of this is my field, of course. I just do this for fun. So I don't know if this sort of a notation is used more in the field of pure mathematics instead of applied mathematics, or if it could be used in certain things like codes, the way computers, for example, send information back and forth. It has to be encoded with a really large number of permutations so people can't easily crack the code. I've heard of numbers like this being used, such as in moves in a game, like how many possible moves can you have in a chess match, or if you have a really large Rubik's Cube, how many possible moves are there to solve it. And then that's related to the Nuth's up arrow notation, or KNUTH', where you use these up arrows for this sort of notation because the numbers get so huge. And none of that's my field, and I don't know much about it, so there's already YouTube videos explaining it. Next up, we have 0 and negative exponents. You can just make your scale here, a to the 0 power, a to the first, a to the second, goes on up to infinity. You multiply by a to go up, you divide by a to come down, or you multiply by 1 over a to come down. And you can see the pattern, 2, 1, 0, then it goes -1, -2. And that's because you keep dividing by you keep dividing by your base to go down. Notice here, this is how you get a to the 0 power, because if you take any number or any base and divide it by itself, you'll get 1. So a to the first power divided by a gives you 1, and that's why anything to the 0 power equals 1. And here, notice that the exponent can go to positive and negative infinity, but the result will always be greater than 0. That is, if you have a positive base. Now, if we take an exponent to an exponent, we can start out here with a to the first, then we simply take that first exponent to the third power, you get a to the third, take that to the third power, you get a to the ninth, because you just keep multiplying your exponent by 3. And likewise, to come down, you multiply your exponent by 1 over 3, or 1/3. Notice here, your exponent will always be greater than 0. The result will always be greater than 1. So you can take 2 to the 1/10th power, or 2 to the 0.01 power. Your result will still be greater than 1. It'll approach 1, but it'll be greater than 1. And next up, decimal exponent. 9 to the 1.5 power will equal 27. You can pause the video if you want to figure out how to do that without a calculator. Otherwise, I'll show the answer in 3, 2, 1. You just turn your decimal into a fraction. 1.5 is 3/2, so 9 to the 3/2 equals 27. Take the square root of 9, then you cube it. Now I'm going to show some scales. Logic on this is you make your scale according to the denominator of a fraction. So in this case, let's say the denominator will be 2, so it'll be 1/2. It goes 1/2 here, go up to 1, that'll be 2/2, go up again, that'll be 3/2. So if you have 1 and 1/2 power right here, or 3/2 power, then you're going to have a whole plus a half, you get 1 1/2. I was showing the logic on this because on the next page, I'm going to make a scale according to the denominator. So if we look at this, we have a to the 3/2 power. That's the same thing as a to the 1/2 power, quantity to the third, which is the same thing as the square root of a to the third power. The square root of a will be what our scale is based on. And one potential starting point for this square root of a, you can actually take the square root of a and square it. You'll end up with a. So you'll still end up with a to the 3/2, just like up here. But notice the square root of a squared. You can actually start with this on the scale, and I'll show how to do that. All right, so we make our scale according to the denominator. So it'll be a scale according to the square root of a. What we do here is we multiply by the square root of a to go up. We divide by the square root of a to come down. So square root of a squared times the square root of a gives you square root of a to the third. A potential starting point here would be square root of a squared, which just means it's a right there. So that means you can go up 3 and down 2. So we start with a, we go up 3, 1, 2, 3. That takes us to the square root of a to the 5th power, but then we have to come down 2, 1, 2. We end up with the square root of a to the 3rd power, which is a to the 3/2, and that's our answer. Instead of going up and then down, you can go down and then up. Go down 2 places, up 3, starting with a, go down 2, 1, 2. We end up with square root of a to the 0. Go up 3, 1, 2, 3. We end up with the square root of a to the 3rd power, which is a to the 3/2. What matters on this, when you're going up, you always have to start with the square root of a to the 0 power, or always start with your denominator, which our denominator is a square root of a. So start with your denominator to the 0 power, and then go up that many units. So in this case, we go up 3 units because 3 is in the numerator of our exponent. So I'd never seen this before. I just thought it was kind of fun and thought I would show it.